Remember we had the example where we had the 10 questions about the year that the first Nobel Prize was handed out or when Bastille Day is, and you picked an answer and then you also gave a range. So for example, I think distance from the Earth to the Moon, my answer was 200,000 miles. My range was 50,000 miles to 250,000 miles. I was making a range where I felt 98% confident that the correct answer would fall within that range. So this is a fairly narrow range. So I felt very confident, 98% confident, that the correct answer was within that range. And in fact, I was right. I think it was 238,000. However, I was only right for 4 of the items. For the other 6, I made a range that was too narrow. So for example, I think the budget of Penn, University of Pennsylvania, I said I thought the answer was 10 mil. The range was 5 mil to 50 mil. Way too small of a range. It was something way bigger. Was it $1 billion even? And so this suggests that I was overconfident. I thought, oh, I think the answer is between here. I should have done a much wider range. So on 6 of these, I should have done a much wider range, but I didn't. And so for many of you that posted on perusall.com, you also circled 0, 1, 2, 3, 4, 5, 6. I think there was someone who said they circled 9. So that would actually show a regular amount of confidence, not overconfidence. But anywhere between 3 and 7, actually 1 and 7 or 0 and 7, would demonstrate the concept of overconfidence. How we frame a problem can influence the way that we try and solve it. So you saw the example in your reading, problem 3, where this is actually an experimental study. And we're going to start first with condition A. Okay. In condition A, participants are told that the United States is preparing for the outbreak of an unusual avian disease that is expected to kill 600 people. 2 alternative programs to combat the disease have been proposed. Program A: if Program A is adopted, 200 people will be saved, which of course means that 400 will die, but that's not stated. So I'm just going to put a little line through it. This is the only thing that's stated. 200 people will be saved. And Program B is there is a 1/3 probability that 600 people will be saved. So everyone will be saved. And a 2/3 probability that no one will be saved. Okay. So that's condition A. The participants who get this condition, they are asked, choose A or B. Now, in condition, actually I should call this condition 1 since that's A and B. So condition 2, we have same setup. United States is preparing for this unusual avian disease that could kill 600 people. And we have 2 programs to choose from. Program C says 400 people will die. meaning 200 will be saved. But again, that's not stated. Just 400 will die. And program D is 1/3 probability that no one will die, 2/3 probability that 600 people will die. Okay? So half of the participants saw these two choices, program A and B. The other half of the participants saw program C and D as choices. Now, because we get to look at this from a researcher's perspective, we know that program A and program C are exactly the same. They're just framed differently in terms of 200 people will be saved, more positive language, versus 400 will die, more negative language. Program B and program D are exactly the same, but again are framed differently. In this case, 1/3 possibility that 600 will be saved is the same as no one will die, and 2/3 probability that no one will be saved, it's a positive spin, versus 2/3 probability that 600 will die. Now, when this research study was done, what happened was in condition 1, people chose program A over program B. And in condition 2, they chose program D over program C. So then, of course, you may be asking yourself, why is it? Why do people pick program A in this condition and program D in this condition? Well, the researchers, Kahneman and Tversky and Kahneman, talk about it in terms of this is about gains. Lives will be saved. And when a problem is presented to us that way, we tend to be very risk averse. So this idea of 2/3 possibility that no one will be saved, that's too risky. And we don't want to take that chance. So we go for something where we can count on a positive. We know that 200 people will be saved. We're going to go with that one, because we're risk averse when problems are presented as gains. However, when problems are presented in this way in terms of losses, people are going to die, in that case, we do take on risk. So we take this chance of this 1/3 possibility that no one will die. We're more likely to be risky, take a risk when a problem is presented as a loss situation. People will die. So hopefully this shows you, this very famous research study, experimental research study, shows you the power of framing. The way you frame a problem can influence the way people try and solve it. Anchoring is another bias that you read about. Anchoring. And the example that they gave was, again, another experimental study where we have two conditions, condition 1, condition 2. And in condition 1, people are told, okay, we know that fraud occurs in companies, and we're trying to figure out how much fraud people think occurs. And so we're going to ask you, do you think that the incidence of fraud is more or less than the numbers we're going to present to you? So in this case, in condition 1, they got two choices, and they had to pick which one do you think is more likely. So is it more likely that fraud is happening in more than 10 in 1,000 companies? Or is it less than 10 in 1,000 companies? Okay, pick one of these. Now, the other condition got a different set of choices. So they got choices A and B as well, but instead theirs was 200, greater than 200 in 1,000 companies, or less than 200 in 1,000 companies. Okay, so typically what happens is that most people think that less than 10 in 1,000 is too small, and they tend to say it is, less than 10,000 is too small, and they think it's more than 10 in 1,000. And if you ask, okay, so what is it? They might guess, I think it's something like 25. Whereas in this condition, most think that 200, greater than 200 is too high. They think it's less than 200. And then if you ask, okay, well, take a guess at what you think it is, they might say something like 60. And so what this shows is that the number that people were given in the prompt influences the answer that they come up with. So you can see that 60 is more than double 25. And the argument is, across many, many studies, is that the initial number that people get, in this case, if it's a low number, it pulls their hypothesis down. If it's a higher number, it pulls it up higher. The tough part about this is that people don't think that the anchor influenced them. They don't think the anchor influenced them. And that is one of our main problems with these biases, is that people don't realize the impact that they're having on them. Another example of anchoring is when you might be shopping and you see, oh, here's an item that's $50, and today it's marked off and it's going to be $25. So maybe let's imagine that we're doing an experimental study. That's one condition. And then another person sees the same item for $12.50. This person thinks they're getting a heck of a deal because they were given this anchor that somehow somebody thought it was worth $50 at some point, so it's $25. That's a great deal. But if you compare 25, if someone else got it for $12.50, $25 doesn't seem like such a great deal anymore. So this is a technique that companies can use to influence your perception of how much something's worth. When they show you the so-called retail value, and it's much higher than what they're going to ask you for, you tend to think that that's a great deal. But if that number was not there, you would base your evaluation of how much something was worth on other things. The quality of the product, how much you needed it, so on.